Kind of pick up where we left off. We were talking about multiple sets, building for localizations. I'm going to give you the following theorem, which I will not prove because it's done in your homework, or you do it in your homework. The last thing we talked about were ideals of the maximal with respect to a certain property. Well, here's an example. Let S be a multiple closed set, I ideal. Suppose we have a multiple closed set. This is, and I want this to, of course, not be empty. Be a multiple closed set, and an ideal that is maximal with respect to the exclusion of S. Okay, so what do I mean by this? Let me point out, this does not mean that I is a maximal ideal. It just means it's big as possible with respect to this property. What I mean is exclusion of S. It means it misses it. There's no overlap between the ideal and the multiplicative set. And if J is an ideal such that I is strictly contained in J, then J intersect S is not empty. This is what I mean by maximal with respect to the exclusion of S. It means it excludes S, it misses S, and any ideal that properly contains it has to touch S in some way. It has to overlap in some way. The proof of this was in the homework, so I'm going to give it as an exercise. Now, the first question you may ask when I give you this really, and in fact, this is one of the major ways that prime ideals are, I didn't even give you. Look at that. Then I is prime. There we go. There's the conclusion. This is one of the most important ways to show prime ideals is growing something that this is a multiplicative set. Now, the first question out of the gate might be, notice I say, if I have such an ideal, it's maximal with respect to the exclusion of S, does such a thing exist? And the answer is yes. And once again, it's one of these Zorn's lemma axiom of choice things. Theory. Simple. Like I allowed you to, in the last homework, I allowed you to reference this. We're going to prove it. Then R be for one, you can do this more generally. If and S and R, this is not empty. A multiplicatively closed set. And I in R an ideal such that I intersect S is empty. So here's your situation. You have some ring R, you have an I, and you have an S. It's a multiplicative set, and it is an ideal, and there's no overlap. This theorem says, then there exists an ideal J with I contained in J and J maximal with respect to J intersect S is empty. So in other words, if there is an ideal I that misses this set S, then I can sprinkle a little fertilizer on I and grow it to a perhaps bigger ideal J that's maximal with respect to missing S. And what I mean by this is, and if I make it grow any bigger, it's going to overlap S. Everybody okay with what this is telling us? Let's prove this. This one again requires the action of choice. So and so. Soren's lemma. So what I need is I need a set of things. Let gamma equal the set of J such that J contains I. J is an ideal. And J intersect S is empty. Okay, I'm creating this set. I'm going to call it gamma. And what gamma consists of is every ideal in this ring that has three things going on. It contains I. It's an ideal. And it's already said that. And it overlaps S, not at all. So its intersection with S is the empty set. Now, once again, I like to make sure that I'm not proving theorems about the empty set itself. Can anybody name something that is in gamma? Or is gamma empty? Is there an ideal at all that is in gamma? Did anybody think of an ideal of R that meets these conditions? It contains I and it overlaps not at all with S? Well, how about the ideal I itself, right? Because we're assuming right out of the gate that we're assuming two things. We're assuming I is an ideal and I overlaps with S is empty, right? So I itself satisfies this rule, right? Because I contains itself, I is an ideal and I overlap with S is empty. So at least there's something there. Gamma is a partially ordered set right? There may be this whole spray of ideals in gamma that contain I and overlap is empty, but it's a partially ordered set under inclusion. We'll apply Zorn's lemma. B, no, every chain in gamma has an upper bound. Right? That's how Zorn's lemma works, because Zorn's lemma says that if you have a partially ordered set in which every chain has an upper bound, then it has a maximal element. All right. So let us build a chain and see if we can construct a maximal element. So let's let the what does a chain mean? Well, remember, when you're looking at a partially ordered set, you're looking at apples and oranges. Might be lots of different kinds of things. A chain consists only of apples. That is, you can compare any two. Right? So what does it mean to be a chain? It means all these guys live in gamma, but there's something extra. If I alpha, I beta are in this chain, then one of two things happens. This is what I mean by they're all apples. Given any two of them, I can compare them. One of them contains the other. Everybody okay with that? Now, can anybody, this is actually the machine that makes us go. Can anybody tell me what I might, what's a good candidate for an upper bound of this chain? An upper bound of this collection of ideals.
Right. One that's everything else is contained in.
Right, and what's the easiest way to do that? Right, because this chain may go up forever.
Union.
There you go. There you go. So let U be the union. What saves us here is I expect a partially ordered set to have all kinds of different incomparable things, but this is a chain, so it's like a stalk. And that stalk may be a stairway to heaven. It may go up forever, but it doesn't matter, right? What I can do is I can take the union of everything in there, and I'm going to call this U. This will be an upper bound. Well, so note, for all I alpha chain, I alpha is contained in U. That for sure is true. So it looks like this is an upper bound, but remember, we need to be a little bit careful. It is true that this looks like an upper bound because it's the union of everything, but we need to know that this upper bound is in gamma. And remember what gamma was. This was the set of J such that J is an ideal, J contains I, and J intersect S is empty. You show that this U actually is a member of this club. That is, it's an ideal, it contains I, and its intersection with S is empty. Actually, the ideal part is the toughest part. We'll show that this is very similar to what we did before. But I'm going to use the ideal criteria. Let me point out that since U contains every I alpha, we already know it's a non-empty set. We have that X is in I alpha, Y is in I beta, and without loss of generality, we will say that I alpha is contained in I beta, because either I alpha is contained in I beta or the other way around. Therefore, X and Y are in I beta. So X plus R Y is in I beta, which is in. So U is an ideal. Generally, I don't expect the union of things to be an ideal. What saved us here is the fact that this is a chain. So I alpha is contained in I beta. 2. U contains I. Need that to be true. But notice that since I is contained in I alpha for all alpha, and U is equal to the union of I alpha, I is contained in U. That was easy enough. And finally, we need to show that U intersect S is empty. Well, suppose there exists X and U intersect S. Since X is in U, X is in I alpha for some alpha. Therefore, X is in I alpha intersect S, which is the empty set. And there's your contradiction. So U intersect S is empty. Any questions on that? Put your name on that and pass it down. Everybody here gets an extra 100. I'll zoom land. Oh, if you're there and watching, I'll give you one too. Nobody has. Oh, that's too bad. Okay. Any questions on this? Corollary. Let me corollary is. Corollary 940. Let I be an ideal and S be a multiple set such that S intersect I is 0. Multiple set such that it's supposed to be an ideal. And S is a multiplicative set such that I intersect is empty. Then we can expand I to a prime that is maximal. Almost probably intersect. Let me kind of draw a schematic diagram of this. Okay. Here's what this theorem is saying. If you have an ideal I and it misses some multiplicatively close set, I can place I inside an ideal which is necessarily prime, which is maximal with respect to excluding S. Right? So anything bigger than this. By the way, this P may not be unique. There may be more than one way to do this, but there's at least one. Let me give you another corollary to this. 949. If R is a commutative ring of identity and I is an ideal of I is an ideal, then I is contained in maximal. You remember this one? This is one of our big early on ones that if you have an ideal in a commutative ring with identity that is proper, then it's contained in a maximal ideal. We proved this as one of our first applications of Zorn's. Everybody sign this paper or write your name on it. We've already proved this. What's the point of me rehashing this? Well, sometimes it's good to see we've actually got new machinery invented, and sometimes that machinery gives new insights to old theorems. Let S be the units of R. The units of R is a multiplicatively closed set because when I multiply two units, I get a unit. And S intersect I is empty. Right? Because no proper ideal contains a unit. So by previous, I can be expanded to a prime P. Such that P intersect S is empty. And when I say expanded, I mean I is contained in P. P is maximal with respect to exclusion of the units. Right? What does this mean? This means if N is an ideal, with P strictly contained in N, then N contains a unit. I agree. Since P is maximal with respect to the exclusion of the units, if you grow it any bigger to some other ideal N must contain a unit. Hence, N is equal to R because any ideal that contains a unit is all the ring. Therefore, P is a maximal ideal. Not just maximal with respect to the exclusion of the units, it is a maximal ideal. Because any ideal that contains it must contain a unit and therefore be R. Notice that this also shows that any commutative ring with identity must have a maximal ideal because I can always give you an ideal that misses the units. 0, right? So take 0 and expand it to an ideal that is maximal with respect to the units, and there you go. Okay. Questions so far? All right. I am going to give you now probably the biggest theorem. I'm going to give you probably the biggest theorem of multiplicatively closed sets, because this basically classifies what saturated multiplicatively closed sets look like. Recall a multiplicative set, if S and T are in that set, then S times T is in there, right? It just is closed under multiplication. It's saturated if it contains all its divisors, right? So if A times B is in a saturated set, then both A and B have to be in there, right? So by the way, any saturated set must contain what in a commutative ring with identity?
And always find an element times the identity.
Suppose you have an element of the set, call it A, assuming it's not empty. A is A times one, right? So one divides it. So any saturated set must contain one. And in fact, more generally, it must contain all the units, right? Here's a characterization of saturated multiple sets. Theorem 914. Let's let S be a multiplicative set, and I want zero to not be in there. Let me make clear, I want S to not be empty, and I want zero to not be an S. The following are equivalent. And this is a characterization of saturated multiplicatively closed sets. One, S is multiplicatively closed and saturated. Number two, the complement of this set, everything that's not in it, is a union of prime ideals. Before I prove this, let me go with a quick example. Here are a couple of multiple sets. Saturated multiplicatively sets that we talked about a little bit last time. Here's an example. Here are integers. This is basically the power of two plus or minus, including the zeroth power, right? Notice this is multiplicatively closed, right? Because when I multiply two powers of two, what do I get? Another power of two. 2 to the third times 2 to the fourth is 2 to the seventh. Everybody okay with that? Saturated. And it's saturated, isn't it? Because this is because I have unique factorization in the integers. Because if I take the prime factorization of any plus or minus power of two, I only get powers of two as its divisors. So, okay, saturated multiplicatively closed set. This is equal to S. What's the complement? Okay, it's basically It's not just odds though, right? Right, because you've got other crap in it, like six, for example. Everybody agree with that? How do you characterize this? Well, uh, multiples. Everybody agree with that? This is the multiples of 5. This is the multiples of 7. This is the multiples of 11. Where Pn is in odd, right? What happens when you take the union of all these? What's in the union of every one of these?
Multiples of any prime excluding 2.
Well, but there are some multiples of 2 in there, right? So for example, 6 is in here and 10 is in here and so forth. Okay, so let me rephrase the question then. What's not in? The only thing that's missing is, think about prime factorizations, right? Anything that is divisible by 3 is in here. Anything that is divisible by 5 is in here. Everything that's divisible by 7 is in here. Everybody agree? And I can go on and on. The only problem I've left out is 2. What are the only things that are divisible only by the prime 2? The powers of 2, right? So the only thing left out of this are the units, which is plus or minus 1, and powers of 2. These things factor only as powers of 2. Anything that doesn't factor as a power of 2 has an odd prime factor, therefore is in this mess. So this thing is the complement of S. So S complement is the union of these prime ideals. So let me do one more example. What if I have this? Complement this, the evens, right? And I can write that as a prime ideal, can I? And again, the complement is a union of primes. In this case, just one prime. Prove this. All right, so let's do 2. Let's do this first. Let's suppose that the complement is the unit of primes. We want to show that S is multiplicatively closed and saturated. So let's let AB be an S. I want to show that AB is an S, so I want to show it's multiplicatively closed and saturated. Right? So with this end, now we have AB and S. Let me write SC this way. So I'm gonna write S, the complement of S as that union of primes. Then for all I in this index set, A and B are not in PI. Right, because AB are in S, so AB is in the complement of this union of primes. So for every I, AB is not in P, right? Therefore, prime is very important here, right? Because remember, if the product of two things are in this prime ideal, that means one of them has to be in there, right? But neither one of them are. This step right here does not work if P is not a prime ideal. Everybody okay with that? Therefore, AB is not in the union of these PIs. So A, B is in an S. Because if it's not in the union, then it's in the complement of it, which is what S is. Okay. Now suppose we need to show, so this shows multiple flows. Suppose A, B is in S. So what I want to do is I want to show that both A and B are, well, actually I just need one of them by symmetry, but I want to show that it contains its divisors. So let's suppose that A is in PI for some I and I. Then, as PI is an ideal, here, this part of it, we don't really need prime, we just need ideal, that's it. AB is in PI, and hence AB is in the union of PI, which is a contradiction. As AB is an S. So S is saturated. Because what we've shown is if it doesn't contain one of its divisors, then it won't. Okay. How about 1 implies 2? This is really kind of the most interesting part. That is, if your multiplicative flows is saturated, then you pick up the fact that this is a union of prime ideals. The proof for 1 implies 2 is going to depend on some of the stuff that we just developed. If you want to show that if S is multiplicatively closed to saturated, then it's a union of complement, union of prime ideals. So let's let X be an SC. 1 implies 2. Basically, my goal here is to show that the complement of S is a union of primes. Note, the ideal generated by X intersect S is equal to the empty set. Yes, I know X itself is in the complement, but why is the ideal? Because if Rx in X is in S, then X is in S as S saturated. So we get a bonus here. If X misses S, not only does X miss S, but every multiple of it does, because the set we're assuming to be saturated. So it's almost like we're cheating, but the set picks up all its divisors. So if R times X is in S, then that means X is in S, which can't happen. So what does this mean? We have the ideal generated by X misses S, and so we can expand this to a prime ideal. We can expand the ideal generated by X to P sub X. So we have X contained in P sub X, where P sub X is prime and P sub X, let me say S. Notice that this last statement, the prime ideal missing S means that P sub X is contained in F as complement. Since it misses S, it must be contained in complement. So I claim F's complement is the union of P sub X. Once I establish this, I'll be done. Because what I've done is I've shown that the complement of S is a union of prime ideals, right? Okay, what do I know? I know these are primes because they're all like that there. How about the containments? Well, notice that since each piece of X is contained in SC, the union PX is contained in SC. So I've got that containment, sure. Also, if X is in SC, then X is in P sub X. So SC is contained in the union. And so this does exactly what I wanted it to. It writes for me the complement of S in terms of this union of prime ideals. Okay, any questions? Okay, so that is the big shebang when it comes to saturated multiplicatively closed sets. Now, I didn't use the word localization in this section. We're going to start on localizations. What is a localization? Well, it's a way to form fractions in a certain sense. I'm going to do this in a more general setting, but we'll focus mostly on doing this in things. Definition. 911. Let R. I'm just going to do a commute ring, and that's an R multiplicatively closed set. And S and R, a multiplicatively closed set. find localization on the set Rx, R cross X. Equivalent relation. So I'm going to take the set R cross S. So these are ordered pairs. First entry from R, second out of whatever the set happens to be. And I do want empty. Let's not be silly. I am going to declare that R1 comma S1 there exists S in S such that S R1 S2 minus R2 S1 is equal to 0. The set of equivalence classes under this relation tilde, sometimes written with R, sometimes written with S inverse R or R. So these are notations that you might see. We're just going to call this the localization of R at the set S. Set S. Okay. Let me ask Bill a question. Here are two fractions that you might encounter in problems. Are they or are they not equal? I assure you out there, people are not. Yes, they are equal, right? How do you know this?
Because they both simplify to 3/2.
That's one way to do it, right? I would have to agree with that. This simplifies to 3/2. This was simplifies to 3/2. Well, what if I gave you this? How would you verify that these two are the same? Yeah.
Would you do like the same method where you like say like the greatest common divisor of like X and Y must be 1, so like at least like they're both in simplest form or something?
Yes, you could do that, but is there something more directly you can do without trying to think about reducing?
See if they're the same proportion.
Right, and how do you verify that?
Say equals less than speed.
Okay, right. Do y'all remember this? Right? Cross multiples have to be the same. Some business like this. This is equivalent to. Correct? That's a super. There's this one little twist with this S here. I'll get back to this. But if that S wasn't there, what does this mean? If you think of this as R1 over S1 equals R2 over S2, this just means the cross multiples are the same, right? This is very reminiscent of this. This extra S is here in case the ring has 0 divisors. It's not something you have to worry about. But it's something that's taken care of. And we'll see why that's true in a moment. But any questions on it? Okay. Well, we will get back to this localization bit on Wednesday. Any questions? I'll see you then.